So we will continue our discussion about scalability of blockchains. In the last class, we talked about the verifier's dilemma, and we said that if the time taken to validate, that is verify a block, becomes very large, then the question which a particular miner has to address is which block to mine on. So if it has received this block BK, it could still continue mining on this BK dash, which is a competing block it created, which points to the parent of BK. Or it can create a block, let's say an empty block pointing to this new one, right, and start mining on this. So it doesn't know what is correct, what's the best thing to do, because this particular block BK may be valid or not. Right? And if it is valid, then mining on this is going to be a waste, mining on BK dash. But if it is invalid, then it's a problem to mine on BK double dash, because this would have been created, if it's successfully mined, it would be created on an invalid block. Right? So this is particularly dangerous to mine on BK double dash, because suppose this miner, like we said M2, actually succeeds in creating proof of work for this BK double dash. Right? What is going to happen is, even before validating this block, he will send it out. Right? And somebody might actually include this in its blockchain, and somebody maybe who's not following all the rules might start mining on this, right? Even if it hasn't finished validating BK. Right? So it's dangerous, because even honest miners might start generating invalid blocks if, for example, they mine on this one. So the verifier's dilemma should be avoided, and what Ethereum does is it creates the it ensures that the gas limit is so little that within a few, let's say 100 milliseconds, any block is going to get validated. Right? So there are a few other issues too which we need to consider. So one of the issues is how much can we, let's say this is the second issue. The first issue could be verifier's dilemma. But the second question is, what are the limits on gas limit? So this is a limit on a gas of a transaction or of a block. And if you think about it, we have in Ethereum, we have blocks coming every 15 seconds. So suppose we are magically able to solve the problem, right? And we haven't yet discussed any solutions. Suppose we are able to come up with a system which allows large validation times of the block, right? So this of course this is at 0 and this is at 15 seconds. Okay, so the interarrival time is 15 seconds. So after receiving this block, we have to validate it. And validation, we said, involves many different things. You have to validate that the proof of work is correct, that the hash of the state in the block is correct, and so on, right? So how much validation can we do after this? So clearly this has to be less than 15 seconds in the current Ethereum, because you don't want to keep validating this block for very long, right? And if each block requires validation time more than 15 seconds, then there will be a pile up of validation, right? So for example, if this took 20 seconds to validate, and this one itself took 20 seconds to validate. We would have to start the validation of this block after we have done the validation of this one. And if this takes another 20 seconds, then clearly we'll be forever in a backlog mode, right? There would be tens or hundreds or even thousands of blocks in the chain which we haven't validated. So that's not good. So clearly it seems that in the current Ethereum protocol, validation time should definitely be less than the average interarrival time. On average, right? And we might think, what if we want to perform a very heavy computation which takes more than 15 seconds? Right? Maybe a transaction, let's say, runs an AI algorithm, right? Or it does some very heavy privacy preserving computation or something like that, right? And why shouldn't it be done, right? Maybe there's an application which requires very heavy computation which lasts, even a single transaction's validation may take more than 15 seconds, right? And so clearly those sorts of transactions cannot be run over here, which is the point I'm trying to bring out, that the validation time of a full block, you would want it to be less than the average interarrival, right? So this is one limitation, and what we would want is computationally intensive transactions which could run at definitely a few seconds, but if we could get even greater than 15 seconds, that would be fantastic. But that seems impossible with the current Ethereum protocol, right? At least you wouldn't want many blocks coming one after the other, each of which has validation time much larger than 15 seconds. Another issue we will have to consider is attacks. So what new attacks are possible? If we somehow enable CITs to be run on an Ethereum-like system, right? So right now, of course, you can't do it because even the verifier's dilemma is a big problem, okay, let alone these other issues over here. But once you change the rules of a protocol, it opens up new attack surfaces. So something which may not have been possible with the current Ethereum may be possible over here, right? So suppose I make the validation time of a block, let's say 15 seconds or even higher, right? What could an attacker do, right? So for example, an attacker might create a block. Let's say that this is the header. And let's say that the various transactions. And let's say that he has a very large transaction which is let's say there is a CIT over here. And this has an error, let's say it is invalid. Okay, so maybe the proof of work is valid, okay, so this might give some power to an attacker. He could maybe put in a very heavy computation over here just to waste other people's time, other people's computation time, right? So other people will figure out that the CIT is invalid only after validating the full block, right? They might they might accept this block. Let's say that somebody has a chain over here, right? And what he might do is he sees the POW is valid, so he starts validating all of these, right? And only at the end over here he sees that this CIT is invalid, and then he has to discard this block. Okay, so this is it's almost like a denial of service attack on the CPU of other miners. So suppose a particular miner has just one CPU, okay, we are just taking a restricted situation. Then maybe there are other blocks also which that particular miner has received, maybe there is another one over here, a competing block. But because this CIT is taking so long to be validated, he has to execute the full thing, and at the end of it he finds that it is invalid, right? So what he could have done with his CPU, suppose he had instead started validating this block, which was a competing one, he maybe would have very quickly validated it and found that it's a valid block. Okay? So this situation would not have occurred in Ethereum, because this particular block could have been validated and maybe found to be invalidated very quickly if you didn't have CITs, right? And so this sort of a denial of service attack would be hard to do in something like Ethereum, right? The current Ethereum. So once we change the protocol, we'll have to consider these sorts of attacks too. Even if we magically figure out how to avoid something like verifier's dilemma, we still have to worry about attacks like this, right? So we will have to think, how do we ensure that if somebody includes a CIT in his block, let's say, how might he be penalized? Let's say if he puts in an invalid CIT for some reason, right? Okay, so we'll have to deal with these sorts of things too when we come up with our protocols. Okay. So the first thing that I wanted to talk about before we go to Yoda, which is our protocol, is something called TrueBit. So TrueBit was a protocol which existed before our Yoda protocol, and of course it gave us some ideas for Yoda, but there were some shortcomings in TrueBit which we were able to overcome, right? But in some sense, TrueBit inspired this problem of computationally intensive transactions, and also gave us some ideas about what to put in for Yoda. So TrueBit is an offline solution. And in the last class I said what is offline. So offline means that the miners do not do the heavy computation. Okay. So suppose there is a block over here and it has many transactions. Suppose one of them is a CIT. So what we are going to do is we are going to offload this computation to some volunteer okay. And there could be subsequent blocks over here. The volunteer does the computation and returns the result somewhere later in the blockchain. Okay, so this is the idea of offline computation. where the miners do not actually do the validation of a particular transaction. Okay, so clearly we already probably are able to see that there could be some issues coming up over here, because normally what happens in Ethereum is you have to execute transactions one after the other, and a particular transaction may require the state of the previous one. So for example, this transaction, right, let's say this one, this particular transaction may require the state which is created by this transaction. Okay, so what is this whole business of offloading? I mean, how can anybody run this transaction without knowing the result of this one? Okay, so there's going to be some limitations. So these CITs which you can run in these offline solutions, at least it's true for TrueBit and Yoda, they have to be somewhat independent of other transactions. So maybe the CIT belongs to a particular smart contract, and somehow none of the other transactions in this block, or at least in all these blocks, will be allowed to mess around with the state variables of that particular smart contract, right, until the result is returned over here. Okay, so there will have to be some restrictions. So let's say that CIT belongs to some smart contract, okay, and this smart contract essentially should not be tampered with until the result of this CIT has been computed and returned by the volunteer. Okay, so I'm going to call this computationally intensive smart contract. Okay, so any contract which potentially has a CIT, I'm going to call a computationally intensive contract, right? And so let's say that this particular CIT belongs to, let's say, CIC1. Okay. So what we have to ensure is that until the result of this CIT is returned by this external volunteer, so the volunteer is not necessarily a miner. Okay. So CIC1 should be frozen you might say locked in a certain way. Until the result is returned by the volunteer. Okay, so that would take care of one issue which we discussed now, but clearly it's putting a lot of restrictions on these CICs, so that it means that other people, whoever has let's say submitted these transactions, those particular transactions shouldn't let's say modify a variable in this particular smart contract. Okay? So what we're going to do here is, if at all a particular transaction is not a CIT, it can be executed directly by the miners one after the other. Let's say this is the only CIT in this particular block. Okay, so the rest of the transactions are executed, and the state is updated and so on as usual. But the CIT is offloaded to some volunteer, and we'll have to figure out who this volunteer is going to be. right? And this particular volunteer will have to return the result in some way, right? And so what is the result? I mean, because there could be 100 variables which are updated by the CIT. So what is this volunteer going to return, right? So the result returned should also have some information, should have all the information in some way of whatever has been modified in the smart contract, right? So the questions that we have to address are who is the volunteer, who will do the computation, this is one question we have to ask. Okay. So what does it mean to return the result? And then obviously you're wondering how do we know that the result that this particular person has returned, how do we know that that result is correct? So how do miners know that the volunteer has done the computation correctly? So this is indeed a very tricky thing, and it's going to involve a lot of effort, you can say, or it's going to become a big challenge for TrueBit and even Yoda to solve. Right? So anybody can say that I'm going to be a volunteer to do the computation, but let's say maybe his software is not updated or whatever, right? Or maybe he does the computation wrongly. Maybe there was a problem with the hardware that he was using, right? So how do we know that he's done it correctly? Or maybe he's just plain malicious, and he just wants to upload false results and give it to the miners, right? So how do we deal with this? So we have to be able to verify the result. Yeah. So we are saying the volunteer need not be a miner. Right? So we just give it to one person. He may not be a miner over here. So how do the miners know that he has done it correctly? So of course the miners are running the regular Ethereum protocol. They're executing these other transactions which are not CITs. Okay. So what TrueBit wants to do is ideally they want to give it to only one volunteer. So that overall the computation in the network goes up, right? If you force everybody to do this computation, then you're going to overload the CPUs of these miners. They will themselves have to have lots of extra CPUs to do these CITs, right? Suppose there are 10 CITs. This here maybe there is one CIT, but there may be CITs over here also, right? Many of them. So many of these CITs may have to be run in parallel. Of course, they would belong to different smart contracts and they'll be updating a different sets of variables. Okay, but if there are, let's say, 100 of these running, you wouldn't want every miner to have 100 CPUs to be able to run them. Ideally, you want one person to do it and he returns the correct result. Okay, but this is non-trivial to do to find out that the result is actually correct, because it could as well be wrong. Okay, so we need some mechanism to find out, first of all, decide who gets to do the computation, and then of course he has to return the result, and somehow we have to be able to verify that the result is correct. So here are the steps followed by TrueBit. So what we want is that only one person, we're going to call a solver, will do the computation. Okay, so anyway, step one is that first somebody called a task giver puts let's say a CIT on the blockchain. Okay, so what this means is the task giver is just some user and he broadcasts a transaction which is a CIT, which requires a heavy computation, right? And maybe for the timing, let's assume that all transactions belonging to a particular CIC, that's a computationally intensive contract, is every single one of them is a CIT, let's assume, or is classified as a CIT, right? So it's very easy to identify these. So somebody puts a CIT in his block, right? And let's say the CIT gets into the block over here. Okay, so everybody identifies which are CITs and which are not CITs, right? And this particular CIT now is included in the block, but nobody does the computation immediately. They just skip over it, and the miners are just going to execute all other transactions, right? So this particular CIC, let's say that this is CIC1, okay, has a storage root which is like a hash representing all the state of that particular CIC. So let's assume that you have state variables of the CIC. So these are all variables, right? And there's a Merkle tree which has all of these as leaf nodes, and the root is what we're going to call the storage root. Okay, so the question is, where is this going to be stored, right? So is it going to be stored with all the miners or not, right? And one option is that yes, in fact, this is stored by all the miners, okay, but what we have to ensure is that no other transaction is going to modify this storage root while this CIT is being computed. Right, so this might be there, but all the miners will not have the updated state. They will have some particular state, right? And only, let's say, when the person who does the computation, the solver does the computation, he will have to say which particular variables are updated, what are their new values, and what is the new storage root, right? So this could be stored by miners. So full state could be stored by miners. Right? Or maybe there is another thing that only potential solvers store this information. let's say the full state of CIC1. And let's say the miners only store the storage root. Okay, so this, of course, we are not going to be bothered so much about these details, but how we implement this, of course, depends on many different factors. Okay. So this is initially when we haven't even talked about the solver and so on, right? But this is how a CIT is put on the blockchain, and there is some state corresponding to this CIC which is kept frozen. Nobody is allowed to touch it, and finally when the result comes back, it will have to update this state appropriately. So this is about how a CIT gets onto the blockchain. The next question we have to ask is, who are these solvers and how do we decide who is a solver for a particular CIT? Okay, so step 2. Okay, so a solver is chosen. So any potential solver can volunteer to do the computation. Okay, so I should say there is a step 0 over here. So anybody can volunteer to be in this pool of potential solvers, and they can do that by maybe submitting a transaction where they put a deposit. Okay, so something like we saw for Buterin's protocol slasher, right? So we said that you have potential people who can sign a block in that particular case. So just like that, here you have potential solvers. So several volunteers can deposit some amount to the blockchain, and that is going to sort of be that's going to be used by the miners potentially to even punish these people if they misbehave. So several people initially deposit some amount to the blockchain, okay, and these are potential solvers. So seems to be some issue over here. Writing. Okay. So initially, of course, before all of this TrueBit protocol runs, any user, let's say of the Ethereum protocol, can go and deposit some amount of money. Okay, maybe there is a smart contract which is used to get volunteers. So anybody can put, let's say, 10 Ether or whatever the amount is, and he can say that I am a potential solver, right? And of course, his identity is not his physical identity, but his identity is from his public key, right? And anybody who has the private key corresponding to that will have to sign messages, right, and say that I am a potential solver. So initially there's a pool of these people who have volunteered, and now uh, any one of them can become a potential solver for this particular CIT which has been submitted to the blockchain. Okay? So how are we going? So the question is, how are we going to choose one of them to do this, right? Because many of them might volunteer. Maybe all of them will volunteer to do this particular computation. So what TrueBit suggests is that whoever wants to do this CIT computation will just broadcast a transaction. So all volunteers will just broadcast transactions saying that I want to solve this particular computation. I'm just going to call these volunteer transactions. So let's say that these are the various volunteers. These are potential solvers. And let's say some of them volunteer. So each of them creates a transaction and broadcasts it and sends it out. Okay, so let's say 3 out of 5 potential solvers say that I want to do that computation. And the question is, we want to choose one of these to become the potential solver. Okay, to become who will actually do the computation for us. So how do we do that? Well, so whoever is creating the next block, so let's say that the CIT gets in over here. Let's say there's a particular window of time. And any miner creating one of these blocks will, let's say, has these transactions in its transaction pool. It can choose one of those. And let's say that this particular transaction gets in over here. It's the first one to get. And in this particular case, this particular node has become the solver, because its volunteer transaction got in first. And of course the rules of the blockchain could be that only one person is allowed to volunteer to become the solver, right? So even though these transactions were sent out into the network by these other potential solvers, their transactions will not get into the blockchain. Okay, the rules can ensure. So this way only a single person becomes a solver. Right, so of course here the miner is the one who is going to decide who becomes the solver, and there's a potential, maybe that it opens up some potential attacks where the miner might himself be a solver, right, and he might give himself the chance to do the computation every time, so because there may be some heavy transaction fees, let's say, in the CIT, and he may want it, right? But anyway, we're going to ignore that for the time being. So the CIT gets into the blockchain at some point in time. Then there is a window period during which one of these potential solvers is going to be chosen as the solver by whoever creates these blocks. Okay. So for example, if this particular transaction had got into an earlier block, this one would not get into the blockchain at all because it is competing with that. Right. So the first transaction of these potential solvers which gets in decides who is the solver, and the rules of the blockchain ensure that no other competing transaction gets it. Okay? So this is how we choose a solver. And now what happens? Well, the solver has to do the computation. Now everybody in the blockchain knows who is the solver. So the solver submits a transaction with a new storage root. So we are assuming that the second option which we had chosen earlier is being used. Okay, so we are saying that only potential solvers store the full state of the CIC and the miners only store the storage root. So the blockchain itself only has to have the storage root of that particular CIC in this case. Okay. So this has been submitted to the blockchain, or actually even I beg your pardon, so maybe I need to take that back. So this would even work in the earlier case. Okay, so right now we only want to know whether the solution submitted by the solver is correct or not. So even the first option where the miners eventually store the full data of the CIC, okay, that too could be used. Okay, so I stand corrected over there. So let's say that the solver submits a transaction with a new storage root for that particular CIC. Let's call it CIC1. Okay. So this too goes as a transaction, and let's say it gets in somewhere over here. Okay, so there are many different blocks have gone into the blockchain after this CIT was submitted. Right? So first the solver was chosen, and now the solver has submitted a new storage root after doing the computation. Right? So he's updated the state variables and updated the storage root and uploaded via transaction a new storage root over here. Now comes the interesting part. How do we know that what he has submitted is correct or not? Right? So what TrueBit says is that anybody can challenge this. So he can challenge a submitted solution. So maybe another potential solver, right? Another potential solver can say, I want to challenge this result. I think that what he's done is wrong. Okay, and anybody can challenge that, and then what we have to do is that we have to be able to decide who is correct. So suppose he does, somebody challenges this. Now the miners have to decide who is correct and punish the wrongdoer. So how is this going to be done? I mean, so even over here, what do we do in step 4? Who is going to challenge, right? I mean, there could be 100 people who want to challenge, right? So how are we going to do this, and then how do they submit their own results? And then the question comes in step 5, how do the miners do it, right? How do the miners decide that who is correct, the solver or the challenger, right? So it's getting more and more tricky as we go into the protocol, right? And first of all, we have to ask ourselves, why would somebody challenge? Right? So one person is chosen as a solver to do that computation. So why would other potential solvers actually do the computation? I mean, they would have to do it at roughly the same time as the solver in order to know that the solver is wrong, right? And why would anybody do it? Because you're going to give all the transaction fees to this particular solver, right? So we have to incentivize people to become challengers. And step 5 is like, how are the miners going to decide who's correct? Because if the miners have to do the full computation themselves to decide which among the challenger or the solver is correct, then we have defeated the whole purpose we started out with. So we said that we don't want miners to do the computation, right? So lots of questions we have to answer. So first thing is how to incentivize challengers to do the computation even after somebody has been chosen to solve the problem, and how to make the miners resolve the conflict without themselves doing the whole computation again. So how can miners decide the conflict without redoing the CIT computation? So TrueBit answers all these questions and it becomes quite elaborate. Right? So when we propose Yoda, you'll see that we try to get around some of the issues and some of the problems that TrueBit has. Right? But TrueBit itself is quite clever in whatever it tries to.